Okay, in this video I'm showing you how to do a paired samples t-test. I'm using an example from Andy Field's textbook. So this is a data set that was provided by the Andy Field textbook. And it's a question about spider phobia or a phobia or anxiety. So the question was, do people react more negatively to a picture, in terms of anxiety, a picture of a spider or a real spider? We have 12 individuals here, and each individual is exposed to both the picture and the real spider. So this is a within subjects design. It's within the same individual. Nothing's changing about the individual except for their exposure to either the picture or the real spider. So we're going to make a comparison between the two. So this is where since there's only two different treatments, the picture or the real spider, this is a paired samples t-test. If there was more than two groups, we'd use a repeated measures ANOVA or some other design that allows for repeated measures. Again, so there's only two here, so this is a paired sample t-test. Both of these are normally distributed. We can actually look at the different variables and just to see if they're normally distributed using the explore function. Just take a look at these, maybe do some plots as well. What kind of plots do we have here? I hate stem and leaf, we'll do histogram. Okay, hit OK. Just take a look at our data. And it's running right now. Not so sure why it's taking so long, but let's see. So, wow. We can call this normal, right? The data, they don't look horribly different from normal. We have a small sample size, so I can see why we don't have this like perfect normal distribution. We can always also look at these values for skewness and kurtosis. Skewness occurs when we have a tail that's extending in one direction or the other, and kurtosis is about how wide or narrow the distribution looks, the hump, right? And these are standard errors. I believe that's what this is. Yeah, standard errors. So we could actually do a test, a z-test, by dividing the estimate by the standard error, and clearly none of these are going to be greater than 1.96, 1.645, or whatever we want to use as our criterion. So we can pretty much assume that we have no violations of normality here, and go ahead and run this analysis. So you notice that what I did to get here was I did an analyze, and then I went to descriptive statistics and looked under explore to get the values that I wanted. So now to run the paired samples t-test, I would go under compare means. Well, we have a variety of different types of t-tests. We want to use the paired samples t-test in this case. Let me reset this because she ran this earlier. So I'm going to highlight both of these and move them into where it says paired variables. So we have anxiety at time 1, or anxiety for the picture and anxiety for the real spider. Under options, we have 95% confidence interval. No, I don't need to bootstrap, and that's a whole different topic we can talk about some other time. And hit OK, and I get my results. By the way, as you are running these analyses, if you double-click the output here, these are the commands that you can use if you want to run these analyses using syntax. Syntax is actually a better way to run analyses than this stupid drop-down tab. The drop-down tab is okay if you have a couple of variables in there, but when you have thousands of variables in a data set, the drop-down tab would be misery. So what you do then is you can copy these and open yourself create a new syntax file, and then paste these in the syntax file, right? Then so as long as things are green and not red, you're okay, and you can actually run this test from here. But what you can do as well is you can save that that syntax for future analyses, where you're doing, you just create your own syntax file and you can do these analyses, change the variables, change the data sets, etc. So that's something I personally like to do. But let's look at this. So we have the mean level of anxiety for the picture is 40. It's 47 for the real spider, so apparently it gets higher, but we don't know if that's significantly different. Here we have the standard deviation, standard errors of the mean, sample sizes, paired correlations, so the correlation between the two. It says here 0.067 is our p-value. In SPSS, sig is the same as p-value. It's a real small sample size, so I'd consider that significant. Mean difference is 7, we know that. There's a standard deviation of the difference, standard error of the mean, our confidence interval, and here's our t-test result. So our t-test result is minus 2.473 because we're using a computer to do this rather than doing it by hand. I don't really care about using a critical value because I get the p-value here. This is a two-tailed p-value. So our two-tailed p-value is 0.031. So that this means that in this case the alternative hypothesis is that there is a difference, right? But it doesn't say in which direction there is a difference. This would be a good test where you would use a two-tailed alternative hypothesis because the null would be that there's no difference in anxiety between the picture and the real spider. The alternative is if you're not really sure, then you would do a two-tail. If you were sure, like you think, oh no, the real spider will actually cause greater anxiety, then you should do a one-tail test. If you did a one-tail test, you'd have to change this p-value. So SPSS gives you the p-value for a two-tailed. So if I want to do a one-tail, I would divide this in half, right? So you just go 0.031 divided by 2. And we get 0.0155. So one-tail probability is even better than a two-tail probability. Okay? Anything else here? And here's your 95% confidence interval. So because it does not include 0, we also know that this result is statistically significant.